Okay, today we start considering one more method of machine learning that is called kernel density estimation. That's a technique for estimation of probability distribution of the random variable. So before we had a few instruments for that. One of the instruments was just guessing, a family of probability distribution that the data probably follows. In, well, most cases that were some normal distributions, so you might recall how we did that when considering, for example, naive bias, or when we were considering MLE when studying statistics. And today we will study one more method. And the other method that we already know that we can use to estimate somehow some probability distribution that our data follows, you might guess it. What is the simplest method, how do you think, that we can employ to estimate some sort of probability distribution?
From ordinary undergrad statistics, we do know that we have a sample, we can plot it in a histogram, and then somehow visually make a hypothesis about what kind of distribution that can be, and then check it.
Yes, absolutely correct. The histogram, it's a method to somehow estimate the underlying probability distribution, and at least we are trying to capture some sort of empirical frequencies of the data points. But there are certain problems with histograms. It's a really nice method. First of all, it's very simple, so you might guess that whatever you have, it doesn't really matter. So any data set that you have, you are taking that data set and you can immediately use the method of histogram to get some sort of result. It's really simple, it's really quick, so it's good. But on the other hand, it has some sort of problems, and what we want to alleviate these problems. So first of all, I want to show you what are the problems with histograms, so what are we trying to make better, and then I will show you a method that basically makes them better, that can be used as a substitution for that histograms. Here is a nice real-life example for you. It's called Galton's box, and you might guess that we have a lot of small balls in here, and when these balls are falling down, they are reflected from some sort of, I don't know what is that, but they are randomly distributed, and we see that when they are falling down, this is some sort of a histogram, so it's divided into some small bins, and these balls, when they are falling in that bins, we can see that they look like a histogram, and the histogram looks like some sort of normal distribution. This is an example for real-life histogram. Okay, histograms, they are widely used, but they are trickier than they seem. First, you should have many samples to get a really nice histogram. And the second thing, and well, depending on the parameters of the histogram, you might get with the same data, you might get very different results. So let me show you a few examples of that you can better feel what are the problems with the histograms that we often have. So here is an example of a histogram in Python. Done very simply, we have a function hist. There are some parameters that can be tuned. For example, I'm setting the number of bins that I want to have, and density equals true means that I want everything to be normed to 1. So the area under all of these bars their area should add up to 1. So when I'm adding up areas of these bars, I'll get 1. If I don't set density true, I won't have that. Okay. So here is an example. What happens when I am changing something in the histogram? So changing, for example, the number of bins, or if I'm moving them just a little bit. And you see the same data gives you very different results. So one result looks like some sort of bimodal distribution. The other one looks like the just one modal distribution. The picture above, I use here so-called reg plot. This is the plot of data for a single quantitative variable displayed as marks along the x-axis. So these small bars, this is basically the reg plot. In some cases, you might want to use that because it looks nice, and you want to use that to represent some sort of distribution when you have a data set. Okay, so let's consider some cases when I have different histograms on the same data. Here is my data set. These orange dots, these are my data points that came from some sort of distribution, whatever it was, and I'm trying to recover that distribution by building some histogram on top of that. And I want to try using different number of bins for that histogram. This is just one bin, so everything was in one, all points are placed in one bucket, and basically nothing interesting can be seen. Okay, let's try taking 2, 3, 4, and you might see that depending on the number of bins, you get very different representation of the distribution. This one looks like bimodal distribution with one mode here and one here. This one looks like more a unimodal distribution. So depending on the situation, on your choice of number of bins, you might get very different results. And of course, it's not what we want, because if we want to recover some sort of distribution with the histogram, we know that there should be some true distribution, and of course we want to be as close as possible to that true distribution. And if we can get different results by just tuning some parameters, that means that something went wrong, so we don't want that. So here is one of the problems with the histograms. Here is the second problem. So here I have a histogram, and I'm considering different data sets, but they are constructed from, let's say, from the same data set by just performing translation. So I'm just moving all points from left to right, and I'm building histograms on top of that points. And I'm trying to consider all their histograms and see what happens. So once again, when I'm moving them, you can see that all the histograms are quite different. Once again, that's not what we want. Because of course you might expect that if I have a data set and that data set was generated by some sort of probability distribution, if I take all the points and just shift them, I will expect to have this new data set to be generated with the same distribution, just shifted to the left or to the right. And of course, if I don't have that with histograms, that's a problem. Here's what we have. With the histograms, we have some sort of problems that we cannot overcome just working with histograms themselves. So we want to change something to somehow incorporate our intuitive ideas of what should not change or how should this instrument behave when and to get some modified histograms. And that's what we will do right now. So that's basically the question that we will try to solve. Here is the, let's say, standard histogram. So I have some sort of bins, and when a data point falls into that bin, I create this sort of square. So the more points I have, the more squares I just stack one on another. So this is a standard histogram. Of course, you might guess that this is the problem. If my points move just a little bit, it will cause that some of the squares will immediately jump to the different bin. So now we are trying to think, what can I do to have some instrument that will allow me to get the same result when the points are translated? So how can I do that? Can you give me some guess of what can I do to avoid this problem? So when my points are translated, I want the overall result to be translated as well. So what should I do? Well, from some sort of intuitive, let's say, point of view. Okay, so you see the problem was that I had fixed bins, and when my point was moving from here to here, I should take, let's say, the square that I had and move it to here. It's a little bit no good, because that distorts the histogram. Because when this point is moving inside, let's say it moves here, nothing changes. If it moves here, everything instantly changes. That's not very well. I want translation to be true. When I translate some point, I want everything to be translated with that point. So from some sort of intuitive point of view, you might think, well, what if I glue together the square that I give to the histogram and the point that I have.
So we move with the step of bin size?
I'm sorry, once again.
So we are moving a point with the step of bin size. So the square moves with it.
Yeah, but we can move with some different step. That's the problem. So we want something to work independently on the step that we make. So the idea, the intuitive idea that we want to get is to collect together a point and the square that we have. So if this is my point, I want to glue square to this point, let's say in the center of the square. So I glue that, and I want to move the square with the point. So if I move it just a little bit, in here for example, I move the square the same amount. So I take a new square and I move it. So now every point will carry its square. And this will give me some sort of that translation property that I want. So I will take a square, I will glue it to the point, and the point will carry that square with its, well, together they will move. Of course, now you might see that there is a little bit different problem. Which one it is? Do you see that or not? It's not like a big problem, it's like a question we should answer to build our map.
We have the spikes of different widths.
Different widths?
So I don't know how to say it, like in the histogram that is on the bottom of the slide right now.
Mm-hmm.
So there are like spikes that some of them are super sharp, the others are very like a little bit fatter than those sharp ones.
Yeah, but I wanted to see the different problem, or rather a question that we should answer to get our method working. That what happens if I have 2 points in here, each of them has a square.
We are transitioning intersection part to top?
Yes, absolutely correct. So we should
see.
resolve the problem of intersecting squares. So what was good with the original histogram? If anyone falls into the bin, I'm just stacking a square on top of the previous squares. So there was no problem. I just knew where to stack them. Now I have glued my squares to the points. It's good because they are now translating together with the points, but you see that they can all overlap. And I should somehow solve the problem of the overlap. And you are absolutely correct that we solve it just by stacking the overlapped part on top of that what we have. And this basically leads us to this sort of, let's say, I'm not sure if I can call that a histogram. It's not a histogram, it's basically KDE that we are right now studying. This is an example of a KDE with so-called top hat kernel. So let us get a little bit deeper into this method and understand what it means and what are those kernels. Here is a picture for you. Here is a point that I have. That's a data point from my data set. X, as you might guess, is some sort of feature. So we are considering just one feature for now. And I'm doing some PDF estimate. So I'm trying to estimate some probability distribution function. And this is my kernel. So this is a function that is equal, for example, to 1 here and to 0 everywhere else. You might guess, if I have this sort of function for each point, so here is a red function for the red point, it's the kernel for the red point, and this is a kernel for the blue point, so here I have it. If I add them together, I will get exactly what I want. So the overlapping part will be just moved on top of that. So I'm just adding these kernels for each of the data points. Just a brief notion for you, it's called a top hat because it looks like a top hat. So here is the picture and here is the kernel itself. Okay, so what now? Now you might guess that if we have these sort of kernels, I'm just some sort of defining a kernel that I want. So some function k, let's say of x, and I'm saying that I want some function that looks like, for example, like this. Now, what should I do to associate it with the data point from my data set? So, let me draw that in red. So suppose I have a data point x1. How do I get from this picture, how do I get this picture? What should I do?
Translate the curve?
Yes.
Between 2 points?
And how is this translation performed?
This is the average of the points. Like, does average axis?
Well, if I have center here at 0, suppose, now I want this center to be transferred to x1. So I need to calculate
x1?
Rather minus, yeah. So x minus x1, and when x is equal to x1, the kernel looks like this. So this is the case. So I'm just taking a kernel from x minus x1, and this kernel is translated and centered at the point x1. Of course, if I have many points, I will use some sort of sum over I, kernel from x minus xi. There is one more parameter that we might want to tune with all these kernels, and I will show you that it has some sort of meaning. That's the width of the kernel. So in some sense, I want to make this kernel let's say, bigger or smaller. And that is performed by taking kernel from x minus, let's say, x1 divided by some parameter h. And this h is the parameter that is responsible for the width of the kernel. This form is the final form that we will use for our calculations. So we will choose some kernel somehow, and after we have chosen our kernel, we will translate it to each of the points and add everything together, and we will choose the width of the kernel and apply it to each of the points. Okay. Here is an example of our old data set with kernel like normal distribution. So I'm taking a Gaussian and I'm adding them together, and I get this sort of picture. So you see that with KDE I can even get some sort of smooth pictures, despite the fact that my data set is discrete. So I have some discrete points, but I can get this sort of smooth estimate of the probability distribution basing on that discrete points. And I couldn't have done that with the simple histogram, because all the histograms they cannot look this way. Okay, so now kernel density estimation. So in order to perform KDE, we need to make our mind about two things. So first, kernel, which specifies the shape of the distribution placed at each point. A bit later I will show you what we have in sklearn. So what are the parameters that you can use, and the kernel bandwidth, which controls the size of the kernel at each point. So now, on every data point xi, we place the function k that is the kernel. So here is an example of KDE performed for a data set. So here you see that each kernel is translated to its appropriate point. It is scaled by its bandwidth h, and these are some sort of coefficients to make everything, let's say, integrate to 1. So in fact, we can substitute some equal factors of 1 over n with widths, and we can emphasize one point against another point. So here is another example of KDE. If you want some more fine-tuning, some more control about which points you want to emphasize, you can use some additional coefficients like these wi that are multiplied by kernel. So that of course depends on what you are studying, and maybe you will need this form. Of course you will want that all this wi summed up to 1, because we want to have an estimate of probability distribution at the end of the day, and we know that that probability distributions, they should integrate to 1. What do we expect from kernel? Can we take any function or not? Basically, there are some properties that we may want to expect from our kernel when we use that in practice. So first of all, of course, we want our kernel to be non-negative. because at the end of the day we will add up everything and we want to have some estimate of the probability distribution. And probability distribution, of course, is non-negative. So basically we will want that. Probably we will want our kernel to be symmetric. It's not a very, let's say, strict condition, but all the kernels that I have seen, they were symmetric. Of course, you want your kernel to be decreasing. Once again, because your probability distribution that you get at the end of the day, you want your integrals to be, let's say, well defined and to be equal to 1. So you will definitely want that your kernel is decreasing, and at the end of the day you can integrate everything. And of course you might want that integral of your kernel is equal to 1, because that makes things let's say easier. So we can normalize normalize the sum of the kernels. Anyway, K has either a compact support or it should decrease sufficiently fast, approaching infinity. Now, what about, let's say, some more general case? At this point, we were considering only one feature, so that was just one-dimensional space. Of course, in practice, you might want to work with something more complicated, with some multi-dimensional space. What should we do in this case? And here is an example for you what we do in the case of many dimensions. Once again, I have the same kernel, so nothing changes, almost nothing changes. But I should somehow place this kernel over the point that I'm considering. And you might guess that I'm doing that, and just by putting in here a distance between point X and point for my data set xi. And when these points are the same, I get 0, I have kernel of 0, and I'm basically centering my kernel on top of that point xi. This is an example of the formulae for the case of the normed space. So if I have some sort of norm in a vector space, that norm induces me a metric. So all norms, they induce some sort of metric. Of course, not every metric can be induced by some norm. So we are considering the case when we have a norm and we can induce a metric with that norm. And we may have different norms, so here is one more example for you. It's a family of norms, so-called p-norms. Maybe you have seen them somewhere before, and this is one more example for you when you where you can use these sort of norms, these p-norms. I will show you a little bit later some sort of picture that will make them a bit more intuitive. Okay, so what about available kernels? Of course, you can choose some sort of your kernel if you wish, but there are some predefined kernels for you in sklearn, and I guess at some point this was an exhaustive list of that kernels in sklearn. So you see a Gaussian kernel, a top hat kernel, Yaponichnikov kernel, exponential, linear, and cosine kernels. And here are the formulae for them. I have dropped out the coefficients that make them normalized to make things, let's say, a bit more simple. And here you might see that Yaponichnikov and cosine kernels are very similar. Can you guess why? Let's take a look at the formulae that we have.
Tymchyshyn is just approximation for cosine.
Yes, absolutely correct. So if I will write some sort of Taylor series for this function, cosine of yx divided by 2h, the first few terms will look exactly like this. So of course they look very similar, and it has some reason. Okay, so everything is defined with the parameter kernel equals to something, and here is the list of to what it should be equal to get you the kernel you want. Okay, so now you know how to do basically the KDE. Now the question is, how do we choose bandwidth? Our bandwidth is some sort of hyperparameter, so it's not trainable, and we should use it. We should choose it beforehand so that our methods work. And the first question that I want to pose and to answer, of course, is this bandwidth really worth considering? So does it change anything? And it turns out that the choice of bandwidth within KDE is extremely important. And that's basically bias variance trade-off. So it's an example of bias variance trade-off, and you will see that the correct choice may change everything. If we are taking a too narrow bandwidth, it leads you to a high variance estimate. It's overfitting. If you choose bandwidth too wide, that leads you to a high bias estimate or underfitting. And you should choose somewhere that one point, that one value of the bandwidth that will make your results more or less, let's say, good. And here are two pictures for you. So this is a picture with low bandwidth, and you see that it doesn't really look like the correct probability distribution that we have. This is the case of the overfit. The most extreme case will be when we have just very small, for example, Gaussian or some different kernel at each point. And here is a very large bandwidth, and you see that you don't get any, let's say, information or any useful information on the distribution. So you don't see that it has 3 modes or something like that. So these are our two problems. Here's one more example for you, what happens when we are changing that bandwidth. At the beginning it looks not very well, and at the end it doesn't look well as well. So we start with heavy overfit, and we end up with heavy underfit. So we should find that one point in between that overfit and underfit to get some meaningful result. And here is one more example for you. Now I will start changing bandwidth, and we will look what happens to all these to the estimate of the probability distribution that we have. So I'm trying to change my bandwidth. I'm making it bigger, bigger, and bigger. At some point it starts looking good, but if I make it too large, everything just evens out and you don't see basically anything in here. So now we see that the bandwidth and the correct choice of the bandwidth is extremely important. So if we don't want to have some heavy overfit or underfit, we should choose that wisely. And there are two classes of approaches to this problem. In the statistics community, it's common to use reference rules where the optimal bandwidth is estimated from theoretical forms based on assumptions about the data distribution. A common reference rule is so-called Silverman's rule of thumb, which is derived for univariate KDE and included both within SciPy and Stats models implementation. The other potential reference rules are the ones based on the information criteria. So you might remember some sort of information criteria I showed you before, AIC and BIC. We have seen them when considering trees and random forests, and this another option is improved Schechter-Jones algorithm, IFG. In the machine learning world, the use of reference rules is less common. Instead, an empirical approach of cross-validation is often used. But you might remember that cross-validation takes a long time. So, in some cases, you may not want to do that because you don't have enough time to perform all that cross-validation. But if you do, of course, you can. Probably any parameters can be chosen by cross-validation. It just depends on the time that you have to calculate everything.
Okay. Can we use like variance or variance of the data to try to restrict the bandwidth size or even estimate it?
Well, I'm not sure if I know about such methods, so maybe you can do something. At least one method is, let's say, more or less close to that. Let me show you this one. When we are performing this choice of the parameters, we want to minimize basically the integral of the square difference of the real distribution and what we have. And in some cases, well, if we perform all that calculations, we will get something like this. And what is interesting in here, that, for example, the Silverman's rule of thumb, it uses, let's say so, we have, in this formula, we have a problem finding this sort of thing. That depends on the real distribution, probability distribution, moreover on the second derivative of that, and we don't have that. But if you suppose that that distribution was normal distribution, I know it's very hand-wavingly, but if you do that, if you suppose, you can get this sort of formula. And here you see that variance that you have in data. So in some sense, yes, you are using the variance in data to estimate the bandwidth of the kernel. But you see that the formula that we have here is quite, let's say, tricky. So yeah, it's variance, but it is multiplied by some different parameters. So it looks a little bit more complicated. But everything comes from here. So we want some optimality criterion to select the parameter. And if you use as one the L2 risk function, that is also called mean integrated squared error, or MISE, you can write some sort of you can use some sort of assumptions. So under some big assumptions on f and k, you can get this expression, and the asymptotic mean integrated square error consists of two leading terms. And these leading terms you are then using to get this sort of formula. That works for any distribution. But you see that these formulas, we are not able to use them directly, since they involve the unknown density function f, or its second derivative f, or second derivative of f. So we should somehow estimate these parameters. And one of the estimations is like this one. If we assume that f is normal, we get this formula. And you see that it contains the variance, so probably that's what you wanted. Okay, so one more example of, let's say, guessing the bandwidth is so-called improved Schitter-Jones algorithm. If we have enough data available and the data is far from normal or multimodal, we can try to use ISG. The ISG algorithm is a selector based on the smoothing properties of linear diffusion processes. And it attempts to find H to minimize the MISE that we had previously, depending on the second derivative of unknown probability distribution f, using some sort of recursive formula. It's quite complicated, so I'm not showing that to you anyway. But you should know that there are some sort of formulae that allow you to do that. And now let's try to start some example of the KDE, and I will show you how that rules work. Okay, so hopefully that works, because sometimes these things get outdated. Okay, so here I'm trying to create a Gaussian mixture model. I'm using different parameters, and here is my probability distribution that I have. Let me tune it a little bit. So that's what I have. This is a mixture model of two Gaussians, and here is the overall distribution that I have. With this distribution, I have generated a data set, and you see this data set down here. Now what we want, let's take this data set that we have and the real distribution that we have, and let's try with this data set recover our real distribution. So can we do that or not? Depending on the bandwidth, we will get different results. So let's try to tune that bandwidth and look what happens. So when I make it smaller and smaller, I get something like this. So this is an extreme case of what?
Overfitting.
Yes, extreme case of overfitting. And this will be, of course, the extreme case of underfitting. Now let me choose the bandwidth of the kernel with different rules. For example, Silverman's rule. So here we have it. It looks more or less nicely, so probably this is a good choice. Let's try ISG. In this case, ISG estimate of the ISG is not so good. Let's try cross-validation. Takes a long time because cross-validation always takes a long time. Oh, here it is. Well, this one or Silverman's, it's two candidates, let's say, for the best result. So here's what we have. So hopefully now you see that changing the bandwidth of the kernel drastically changes the overall result. So you have very different curves depending on what you have and what bandwidth you choose. And of course, you see that these rules, they are more or less somehow working. Of course, you can change your kernel. For example, if I use top hat kernel, I will get something like this. Looks not so good, but well, ISG was overfitting anyway. Let's try cross-validation. Wow. Seems like something went wrong, but anyway, it created a picture for us, and here it is. So looks more or less of what we can expect. Okay. Now a few just more examples. So here is a 2D example. I will show you a 2D example, and of course in practice we will want to consider many dimensional examples. I have already shown to you that in these cases we just use distance when we are computing all that kernel thing. So when I was computing a kernel for 1 point, I was using x minus xi divided by h. For multidimensional case, I would like to use distance between x and xi divided by h. So that's more or less natural. So here is an example of distance in a metric space called P metric that you may want to use when considering, let's say, different problems. In case of p equals 2, you have Euclidean distance. In case of p equals 1, you have so-called Manhattan distance or city block distance. And in case when this parameter p goes to infinity, you get so-called d infinity or infinity distance that looks like this. So now I want to show you some pictures to get better grasp of that distances. Here is a picture for you that shows you how the balls of different radii look in a metric space with the P metric. They have radii like 1, 2, 3, and 4. And here is, of course, a well-known case of Euclidean distance. And we see here a very familiar picture of just balls of different radii. Now, what will happen when I make these P smaller and smaller? So when I'm making it smaller, first at p equals 1, we get to something like this. So this is a Manhattan distance. We have seen that distance when considering what? Who can remember?
Like L2 or I don't remember how to say it. So when we were reducing features.
Yes, regularization. Yeah.
Regularization.
Yeah. So we were performing L1 and L2 regularizations, and this was the case of L1 regularization, and this was the case of L2 regularization. If you change this P further and make it closer to 0, you will get pictures like this. And if you make it bigger and bigger, you will get pictures like this. Probably you might guess that in a limit, you will have these sort of squares. But that will be the limit when p gets to infinity. Okay. What else do I have? Here is an example of KDE for 2D points that you can use to play around and just to gain some intuition how that works. As always, I have moved the code that performs basically the work or the KDE to the outside so that you can see how it is called. So here I'm just creating kernel density and setting some parameters and performing fit. Okay, so let's try to start the thing. And see what happens. So here I'm choosing a kernel, metric, bandwidth, and I'm adding some data points. So let me add some data points. and perform KDE. Yes, it still works. And here you see how it looks up. This sort of two Gaussians. Now let me change metric. For example, I want Manhattan metric. You see they are, let's say, spiky. To see the difference between metrics better, you can use, for example, small number of data points. So let me put just, I don't know, 4 data points, and when I'm using within metric, you will see these sort of circles, and when I use Manhattan metric, you will see something more square-like. Or we can use infinity metric. And get something like this.
This kernel density thing is used only for visualization, or it could give also some things for data analysis?
Yes, it is not only used for visualization, but in some different cases as well. At the end of the lecture, I will show you at least one case of using KDE, for example, as a not so naive bias. So you remember we had a naive bias approach, and the problem with that approach was that sort of naivety. We were trying to transform our probability distribution into a product of different distributions, because we didn't have enough data to estimate something in there. But when having KDE, you can perform that estimate with KDE, and you won't need that naivety. So in some cases, of course, you can use KDE as estimation of probability distribution, not just for visualization, but as the part of different methods. Okay. Yes, we are basically almost done. So let me quickly get through all the rest things that I have here for you, and that will be everything. Just a small, let's say, reminder. If you remember the previous lecture about mixture models, you can treat KDE in some cases as a mixture model, but it's a mixture model that carried to extreme. If you remember correctly, I had some sort of data point, so I had a data set, and I was choosing the number of components. So I might have I don't know, 200 points, 2000 points, and choose, for example, 2 Gaussians to fit in there. Here I had carried the mixture model to extreme, and I have associated a Gaussian with each of the points. and here you see the result. So you can treat that in some sense as a mixture model. One more analogy for you. It's a blur analogy. So we have seen that histograms may be misleading. They are grainy, and they discretize continuous data. PDF estimate could be kept smooth by using Gaussian KDE or some different smooth kernels. The idea is similar to Gaussian KDE, is involved in Gaussian smoothing of images. So you might recall from maybe some different courses that if you are working with images, you quite often use the operation called convolution. And that sort of convolution is basically an example of KDE. So here is an example for you of an image that is processed with the Gaussian kernel, and I'm getting some results just by convolving it with the Gaussian kernel. So here is original picture, and here are results by convolving it with 15 by 15 Gaussian kernel and 35 by 35. So you might see that it gets really blurry. And okay. And let's first sample our image, keeping 1 pixel out of 10 along each dimension. What we get is some sort of analogy of getting a histogram. And you see that this sort of histogram looks like this. So this 10 by 10 pixelization or resampling looks not really nice. But if we perform a Gaussian blur afterwards, we can regain some smoothness. And probably if you have studied some methods of, I don't know, image processing methods, you saw that you very often use Gaussian blur because you don't want to have some, I don't know, some very sharp gradients on your image or something like that. So it's very, very often used operation. And here is one more point of view, like KDE as a convolution. We can look at KDE as, we can see it as the convolution of the function representing the density of the samples with the kernel K. So in continuous case, if you remember, a convolution looks something like this. Of course, what more often programmers use is the discrete case of the convolution. And what I want to mention here, that convolution is very often used together with the Fourier transform. Can you tell me why? What's so special about Fourier transform and convolution?
If we pointwise multiply two Fourier transformed signals, it is equal to convolution of those two signals.
Yes, absolutely correct. So the Fourier transform of the convolution is equal to the product of Fourier transforms of the original functions. So in the Fourier space, the convolution just transforms into plain old multiplication. And that's really good. What else is really good? That we have discovered such a nice thing as fast Fourier transform. That's a procedure that takes just O of n log n operations. And this is really nice. If we didn't have fast Fourier transform, we wouldn't have many things that are today for us very, let's say, familiar. Without FFT, we wouldn't have HPEG format for images. We wouldn't have MP3 format for our music, and so on and so forth. So it's a really great algorithm, and one of its nice features is that we can perform it very quickly, and since we perform everything quite quickly, we can perform convolution quite quickly. That's really good. We are just doing Fourier transform, multiplying one more Fourier transform, and we get what we want. Okay. There are several options available for computing kernel density in Python. The question of the optimal KDE implementation for any situation, however, is not entirely straightforward and depends a lot on what your particular goals are. Here are some implementations of KDE that we have. So you see that you can find KDE in SciPy, in stats models, in scikit-learn, in KDE-Py, and so on and so forth. So many different implementations, and they may differ a little bit in their algorithmic nuances. So some use fast Fourier transform, some don't use. Some use KDE tree data structure, and so on and so forth. And of course, I want you to remember that the performance of the algorithm depends on the number of points on the kernel, on the bandwidth that we saw, and on the tolerance that you aim to achieve. Here are two links to articles that I have here for you, and you can check them for comparison of different algorithms, and maybe you can find something suitable for your needs. Now let's get to examples. The first example is the graphical representation of data. Very common used in practice. So let's try to get that. Here you have, let's say, two animals, Bradypus variegatus and Microsimus minutus. Let's try to take the data set that shows where do they live. So we have a bunch of points, and each point is basically an event of seeing one of these animals somewhere, and let's try to put them on map. So here is the map. You may see it South America, and you see all these points where someone has seen them. But looking at these points, it's really hard to understand what we see. So yes, some points are here, but it's not very informative. So it doesn't a very good idea of the density of the species, because points in the species range may overlap one another, and we might just not realize what are we looking on. Of course, you might say, let's make these points smaller, but what would you do if you have a very large data set? So you will have there, I don't know, thousands or millions of points. You'll need to find some better solution. And the better solution is using KDE. So here is an example of using KDE. And now from these sort of images, you can immediately gain some information on where each of these species is more common. So just looking at this picture. One more interesting thing that I want to show you is the metric that we use. Since we all are living on Earth, and you know that it has some sort of form of some sort of sphere, we might want to calculate our distances, not with Euclidean distance, but with something more complicated. For example, if I have point in here and in here, I may not want to calculate the Euclidean distance, but I want something better, something like this. And here is the formula for this distance that we have on sphere. Looks quite complicated, but you can make it, let's say, a bit more compact. So here you see that d is the distance between points, while phi and lambda are latitude and longitude of the points on the sphere. Let me check, maybe. Oh, I don't have it here. Okay. The interesting thing is that all these expressions under the square root in here, it's basically the formula of the Haver sign. And here theta, it's the central angle between 2 points that you are interested in. So if I have a sphere, here's 1 point, here's another point, and the central angle between them, you can use that in you can substitute that into this function, and you basically get everything that you had in here under the square root. It may be, I don't know, maybe interesting for you, because what I wanted to show that there may be more trigonometric functions than we use today. So today we often use just, I don't know, sine, cosine, tangent, maybe cotangent. But if you look in some old books, you will find there something like, I don't know, maybe 12 such a functions. And you will have there something like Haver sine, Haver cosine, and so on and so forth. The reason is that today we have calculators, and it doesn't really matter whether we should calculate this sort of formula or something different, so everything is easily calculated with the calculator. But in that old days, when they had just some sort of tables and books with all these numbers, people have used much more different trigonometric functions, because it's much easier to get a number from the book than to get a few different numbers, multiply them, square something, and so on and so forth. Of course, at each step you can make an error, because everything is performed just by hand, and you don't want that, so everyone was trying to simplify the work, and they have created much more functions than we use today. One more example of visualization. It's a very well-known data set with irises, Fisher irises. Here I'm considering just two different species of the irises, and here is example of visualization. I guess there are three features, but I have visualized two only, and here is the visualization of sepal width and sepal length. And you see that KDE gives us some information on these parameters, and we can gain some intuition what to expect. So if I have some request, for example, what is that iris with these sort of parameters, or these sort of parameters, or these sort of parameters, I can just, looking by these plots, make some educated guess. Okay, an example that you were asking me about, not a visualization. It's not so naive bias. So for naive bias, a generative model is the simple axis-aligned Gaussian. With the density estimation algorithm like KDE, we can remove the naive element and perform the same classification with a more sophisticated generative model for each class. It's still Bayesian classification, but it's no longer naive. What was the problem that we had? So we wanted to know, when performing naive bias, we wanted to know what? The probability of getting class C, yeah? Okay, so when features are equal to something. So for example, feature 1 is equal to x, something. Feature 2 is equal to y. Maybe I can regrow that better. Class C, feature 1 equal to x, feature 2 equal to y, and so on. We couldn't get the information that we need because we didn't have enough data. So what we were trying to do, we used the bias formula. So the probability of having feature 1 equal to x, feature 2 equal to y, and so on, in case of class C, multiplied by probability of class C, and divided by probability of getting these features independent on class. So the expression in the denominator we wrote like some sort of sum and so on and so forth. But what now? In case of naive bias, we split this probability in a product. So we were splitting it and transforming this P into a product of different probabilities. But now we performed that because we didn't have an instrument to estimate that probability distribution. So we were assuming that all the features are independent, and I told you that this independence or naivety is one of the biggest minuses of the naive bias that we have. But now we have KDE. What can we do? Do you have any ideas?
You can estimate this probability.
Yes, we may estimate it right now. Because we have our data set, I can take from my data set all the points corresponding to class C that I'm interested in, and I can estimate that probability distribution with the KDE. Let's look what happens. When performing all these, okay, I don't want to get into all this code. I just want to find some sort of result. Here it is. So if we choose bandwidth, let's say widely, we can get the perform the accuracy of almost 97%. That's the accuracy of classifying numbers from MNIST. So I have that handwritten digits in MNIST. I'm trying to classify them, and I can get the accuracy of almost 97%. If I use a naive bias, so here is just Gaussian naive bias on the same data set, so same digits, I can get the cross-validation score of almost 82%. So you see that compared to naive bias, we were able even to get something much better. And the additional benefit of such a generative classifier is the interpretability of results. For each unknown sample, we not only get a probabilistic classification, but a full model of the distribution of points we are comparing it to. And that's really good. Okay. Of course, we can do some further improvements of our KDE classifier model. So what we were classifying, we can allow the bandwidths in each class to vary independently. That may make results better, and we can optimize these bandwidths not based on their prediction score, but on the likelihood of the training data under the generative model of each class. So we can even make sure there are some points to make everything better. Okay, and I guess the last example for today, the example of 1849 Broad Street cholera outbreak visualization. So there was a severe outbreak of cholera that occurred in 1849 near Broad Street in the Soho district of the city of Westminster, London, in England, of course. And that pandemic was happening worldwide. That was at that days quite, let's say, that happened time to time at those days. And the outbreak I'm talking about killed 616 people and is best known for the physician of John Snow and his study of its causes and the hypothesis of germ-contaminated water. And that's a really interesting case because you might guess that at those days we had a very different, let's say, knowledge in the area of medicine and so on, and the people were believing that the cause of that pandemic is some sort of particles in the air. So they thought that something is wrong with the air and so on. So the idea of the contaminated water was quite novel at those days. Let's look how he came to that conclusion and how can we get the same conclusion as well. Here are two pictures for you of Jon Snow. The one that looks more like English gentleman, that's the Jon Snow we are interested in. So what he did, he took a map of the area and he put points on that map that signified the number of casualties at those houses. And he overlapped that map with the map of water sources that they had at that time. And he was able to identify the source of the outbreak as a public water pump on the Broad Street. Here is an example of that overlapping data. So here you see water pumps everywhere in the area, and here you see points that signify the casualties. And if you perform a KDE, it becomes quite obvious that there is some problem with this pump. So he was able to, from that he was able to draw a conclusion that something is wrong with the water and they should do something with that water. And the solution, as I guess, was quite simple. I guess programmers will like it. Just someone has come to that pump and to remove the handle so that no one can use it anymore. And that was all. So the outbreak stopped just by removing a handle from the pump. Okay. With that being said, today we have considered a method of kernel density estimation. KDE is a non-parametric estimation technique that can be used for probability density function estimation, data smoothing, and interpolation. Basically, it's a method to get a continuous distribution given a set of discrete points. So you have a set of discrete points and you get some sort of distribution from that. We have seen that when doing KDE, we really want to know the bandwidth of the kernel, because that may change everything heavily. We can get from heavy overfit to heavy underfit. And we have seen at least a few rules that allowed us to choose that bandwidth and to get some more or less appropriate results, like Shitter-Jones algorithm or Silverman's rule of thumb. And we have seen that this method of estimation of probability distribution can be used as a part of different methods where you need a probability distribution of something. For example, in naive bias, we had a problem with the distribution because we didn't have the probability distribution for our points, but we were able to estimate that with KDE and use it as a part of the naive bias in here. Okay, and here is nice final picture for you. I guess the pressure, it's distribution of pressure all over the Earth. So of course you might guess that we cannot measure the pressure at each point. We do that just at some special locations where we have our stations that measure different parameters like temperature, pressure, and so on. But if we want to estimate the distribution all over the globe, we should perform that by some methods, maybe even KDE. Okay. If there are any comments, questions, please. Okay. Yes. No comments, no questions. Good. I guess with that we can finish. And and see you next Friday.